Algebra. Algebra 1. You ready to go? Let's go. We are doing lesson 21 today. We are comparing linear and exponential models yet again. The point here is reviewing what we've learned and comparing and contrasting the two functions, and we're going to solidify your understanding of the two functions. Learning how to differentiate between the two functions, recognizing a constant rate of change or a common quotient, etc. So our homework's going to be a lot of tables and graphs, but it's review. So if you're not sure what's going on, now's your chance to make sure you understand it. First of all, let's look at this table. So this table is going to allow us to compare linear and exponential models in a bunch of different ways. It's going to remind us what linear and exponential models are, and it's going to allow us to easily see the difference between them. So you can either be given the example or write your own model, but I'm going to give you, actually typed out, not my handwriting, example of each type, each linear or exponential model. So go ahead and write yours down because you need to know this, and you can refer back to it when you do your homework. Cool? So first of all, our linear model general form. The next slide is going to have everything in a nice typewritten form. So I will try to fit everything in here in handwriting. That is my linear model. F of x equals ax plus b, where a would be considered your constant rate of change or your slope, and b would be considered your y-intercept. I'm going to keep going down the linear model. So a is your slope, constant rate of change. Please know the next slide is going to have this written, typed in much clearer. But I want to talk through it too. B is your y-intercept, or the f of x value when x equals 0. Our example would be f of x equals 2x plus 3, where my constant rate of change is 2, and my y-intercept is 3. So since my y-intercept is 3, I can start at 0, 3 to find f of x plus 1. I'm going to add 2 to f of x. So for my table, I'm going to start with 0, 3. And for my next point, I'm going to add 2. For my next point, I'm going to add 2. For my next point, I'm going to add 2. A plus 2 pattern. Our exponential model is f of x equals a times b to the x, where a is your y-intercept, or the f of x value when x equals 0. We also called it our initial value. And then b is the base or the constant quotient. We calculated b. Oops. And I'll show you how to do that again. Awesome. An example would be f of x equals 3 times 2 to the x. If something is doubling all the time, we would put a 2 in for b. My initial value would be 3. So starting at 0, 3 to find f of x plus 1, the next term, multiply f of x by 2. So I'm going to start 0, 1, 2, 3. F of x, my first term is 3, multiply it by 2, multiply it by 2, multiply it by 2. Cool. I promised you much more legible. Go ahead and push pause and make sure you have everything written down correctly, okay? When you're done writing it down, go to the next slide. Some example graphs. Again, the next slide is going to be all typed out. 1, 2, 3. We don't have a 4 term. 2, 4, 6, 8. So remember my y-intercept was 3, and we're going up a constant rate of change of 2, so it's going to look very similar to that, where 3 would be at, let me check my table again, 3 would be at 9. So that's not right, because 9 would be up here. Okay. That's linear. Here's exponential. 1, 2, 3, 4. We need bigger numbers. Beautiful, if I say so myself, which I shouldn't. Again, my y-intercept is 3, or my initial value, and my maximum is 24. So that's going to be right about there, and we're going to curve down. Beautiful, huh? An example, story problem. Let's see. At the airport, it costs $10 to park your car plus $3 each day. So it would be f of x equals, oh, we should really use the example with the numbers we're given, right? Sorry. So at the airport, it costs $3 to park your car initially, plus $2 each additional day. That would be the 2x plus 3, right? This one, exponential growth, so I'm starting out with 3. Gosh. Well, we're going with one in the book. Sorry. There are 3 goldfish in the tank. Not creative at all. And the population doubled each month. So here you go, written much better. We talked about bank account, earned, $2 a week as allowance, goldfish one I used, blah. Push pause, make sure you've got this in there correctly. All right, so let's try some. What we need to remind ourselves right now is, before I do this example, with linear equations, we're going to have a plus or minus pattern. And for exponential equations, exponential, we're going to find our common quotient. That means we're going to divide our x plus 1 by our x. Well, no, let's not do that. Sorry. Our second term by our first. And if we get a common quotient, we're exponential. Here, we're going to check the plus or minus pattern, and that means we're linear. So for each one of these tables, we're going to head and figure out our rate of change to see if it's right. So I'm just going to subtract. 1 minus a negative 3 is 4. 5 minus 1 is 4. 9 minus 5 is 4. 13 minus 9 is 4. So we have a plus 4 pattern. I don't have x equals 0, so I need to figure it out so I can write my equation. So if x were 0, I'm going to subtract 4 more and get minus 7. So now I can write my equation. F of x equals plus 4 pattern minus 7. So that plus 4 pattern is our a term, or our slope, and our y-intercept, or what our value is when x equals 0, is our b term. Here, if I tried to do the subtraction again, 6 minus 2 is 4. 18 minus 6 is 12. That didn't work. Okay, it doesn't work. You have to check it to see if it works, and it doesn't. So what we're going to do here is, let's see, the plus and minus pattern failed. So let's try the common quotient. If you remember when we learned this, it was the r value. I can do 6 over 2 is 3. 18 over 6 is 3. 54 over 18 is 3. 162 over 54. Guess what it is? You got it, 3. So my r value, my common quotient, is 3. I know what I'm starting out with. That's my initial value. Therefore, f of x equals my initial value, common quotient, to the x. And it works. Works grand. Nice job. All right, Terrence looked down the second column of the table and noticed that 3 over 1 equals 9 over 3 equals 27 over 9 equals 81 over 27. Because of his observation, he claimed that the input-output pairs in this table could be modeled with an exponential function. Explain why Terrence is correct or incorrect. If he's correct, write a formula for the exponential function that generates the input-output pairs in the given table. If he's incorrect, determine and write a formula for a function that generates the input-output pairs given in the table. He's incorrect because part of the rule is these have to go by 1. My x values have to increase by 1. So this have to be 0, 1, 2, 3, 4, and these are constant. Therefore, it would be f of x equals 1 times 3 to the x. But these are not, they don't increase just by 1. Okay, the distance between the consecutive x values is not 1. Therefore, you can't do it. Right? Okay. A river has an initial minnow population of 40,000. That's my initial value. That is growing at 5% per year. Due to environmental conditions, the amount of algae that minnows use for food is decreasing, supporting 1,000 fewer minnows each year. This is initial. Sorry. Okay. Currently, there's enough algae to support 50,000 minnows. I'm not going to have enough room to do my work, am I? Is the minnow population increasing linearly or exponentially? Is the amount of algae decreasing at a linear or an exponential rate? In what year will the minnow population exceed the amount of algae available? Okay, so looking at The amount of algae that minnows use for food is decreasing, 1,000 fewer minnows each year. So that one is linear, because each year it's the same amount decreasing. Linear decrease, right? The minnow population, on the other hand, is exponential increase. Whenever you talk about a percent increase each year, that would be exponential growth. Let's see, so I can currently support 50,000 minnows, which means next year I would be able to support 49,000 minnows. The next year, 48,000 minnows, etc. Because the first year I have, or the initial, that's up here, I'd have 40,000 minnows. The next year, 40,000 times 42. So the next year I have 42,000 minnows. Let's write it in the right spot. Initially 40,000. The next year I actually have 42,000. The next year 44,100. So this is decreasing and this is increasing, right? Let's see, you still have the problem in front of you. In what year will the minnow population exceed the amount of algae available? So my minnow population, the equation is 40,000, 1 plus my rate to the time, or the x, it doesn't matter. And my algae population we can do f of x equals g of x equals, my initial was 50,000, right? Minus 1,000x. I could really get rid of a lot of these zeros, but that's okay. So for what year is one bigger than the other? We don't know how to solve for exponential variables yet. I'm going to make that an x. But we can guess and check. So minnow population greater than algae population. Let's see, what can I do mathematically? Oh, I missed a zero. Not much. I could divide by 40,000, but that just gets messy. We'll go ahead and try it. If I divide one thing by something, I divide everything by something. So that cancels out. I have 1.05 to the x greater than 1.25 minus 0.25x. Now I'm just going to start plugging in some x's, and I see we did 3 years on the last page, or the last slide, so let's try 4 years. So if x equals 4, 1.05 to the 4th power gives me 1.21, and then 0.25 times 4 is 1. 1.21 is greater than 0.25, so it looks like that's the year. I'm going to double check with x equals 3, the 3rd year. Oh, hold on. Calculator error. So 1.05 raised to the 3 power is 1.16. 0.25 times 3 I have 0.5. Looks like x equals 3 is correct too. I see my mistake. I'm going to fix it in purple, okay? This would be 0.025, which would make this 0.1. Oh, wait. .15, sorry. Still, x equals 4 is true, but this one's not going to be correct. So 0.025 times 3. 1.175. So this is false. So in year 4, it looks like my minnow population is greater than the algae population that's going to support it. Therefore, that's when your minnow population would exceed the amount of algae available. So sometime after the 3rd year, the 4th year hits, and that's when all awfulness breaks loose. That was fun. So, using a calculator, Joanna made the following table and then made the following conjecture. 3x is always greater than 1.02 to the x. Is Joanna correct? Explain. Well, this is exponential, and this is linear. Exponential will, at some point, exceed. So exponential growth always exceeds linear at some point. Always. And actually, I just figured it out. I just graphed it. But 1.02 to the 500 is about 19957, but 3 times 500 is 1,500. So it does exceed eventually, always. All right, there we go. Input-output pairs. For every 2 inputs that are a given distance apart, the difference in their corresponding outputs is constant. So we've got a linear function. For every 2 inputs that are a given distance apart, the quotient of their corresponding outputs is constant. Therefore, we have exponential. Okay, g of x equals mx plus k is your linear. F of x equals a, b to the x is your exponential. For this one, when b is greater than 1, we're growing. When b is less than 1 or between 0 and 1, it's a fraction and it's decreasing. But that's our summary. Cool? Cool.